Okay, time now for another video here. Today's video is about work and power. And before we get started, I give a little precursor here. To do work, you need energy. So work and energy are going to be related to each other. And so this is a good time to bring that topic up. And when you start talking about energy, there are all kind of social and economic impacts to energy you can imagine. But that's a good thing to be thinking about already. And as always, it's good to take the topics that we give you and think about a broader context and how they tie into things in the real world outside of the physics classroom. And certainly energy is a big one in that respect. Okay, so work and power is the topic for today. And we're going to first start out with the idea that we know these terms in everyday usage, but in physics they have particular connotations. So for starting off, we'll talk about work, and work is the force multiplied by distance. So there has to be a force involved for work to happen, and also some distance over which that force is supplied. I'm going to turn the lights back on. I think I am. All right. Hey, I'm back and the lights are back on here. All right, so work is the force multiplied by the distance. So that's a good start of it. Yeah, force alone is not a work, but if you are supplying a force all day long without any distance involved, then there is no work involved. Force itself is not work. Okay. So we introduce a new unit here for work, and that is the joule. And we'll later find out that that's also the unit for energy. Okay, so here's an example, a very basic example. 15 newtons is used to push a stalled car. If you've ever pushed a stalled car, you'd rather be doing it on flat ground instead of uphill. And I also suggest putting it in neutral if I had to push a car a couple of times. But this is very straightforward calculation here. There's a person pushing the car. And what do we got here? The force is 15 newtons. The distance is 35 meters. And we simply multiply the force times the distance. 525 joules worth of work was done. So that's very, very straightforward. Remember, though, or something to be aware of, is that the joule is a derived unit. And, the Newton was also a derived unit, derived out of kilograms, meters, and seconds. The joule is derived out of newtons and meters, so you have to be in newtons and meters to have it be work in joules. Okay, so here's another concept that we can think about, and they call it lifting weights. So if you are lifting weights, the force that you have to supply is equal to the weight of the object. So that's a concept to be talking about. Here's a person lifting up a car in their room. Kind of wonder how they got the car into the room in the first place. But anyway, that person would have to be supplying a force equal to the weight of the car to lift it. Okay, and we know that weight is the mass in kilograms, again, because we're dealing with derived units, multiplied by the acceleration due to gravity, 9.8 meters per second squared here on Earth. Okay, so how about this? How much work is done on a 500 kilogram object if you're raising it 10 meters? Well, first of all, we would have to talk about the force. The force is the weight. So we can find out the weight by multiplying that mass, the 500 kilograms, by the 9.8 meters per second squared. So 4,900 newtons worth of force is involved. And since work is force multiplied by distance, we can now find out how much work is done. So I've put that into scientific notation, but basically 49,000 joules worth of work. So there's another example for you. And let's see here. Okay, so let's see. Another concept involved here is that the work and for the work to be calculated correctly, the force and the distance have to be in the same direction. So here is a staircase, and that's a pretty interesting looking staircase. But when you're carrying something up a staircase, of course you supply a force that is the weight of the object. But your force, kind of like the normal force, goes upward while the weight is going downward. And that should make some sense there. So your force equal to the weight is in the upward direction, but a staircase is going both in the upward vertical direction and the horizontal direction. So the concept here for this type of problem is that it's only the upward or vertical direction that matters. So in walking up a staircase, this staircase here is a little safer for toddlers. That last one can be a little dangerous for toddlers or maybe small animals. But the horizontal distance doesn't matter. So really all that matters is the vertical direction, the force, the distance in the vertical direction. So here's an example, and you know what? I should have done this for the other examples, right? Why don't you pause and see if you can figure out what the answer to this one is. Okay, well, welcome back. And what do we got here? Work is force multiplied by distance. The force is 10 newtons, and the upward direction, the vertical direction, is 15 meters. So 150 joules worth of work is what we're talking about there. And there we go. Okay, so here's another type of example. Now, we've already got the concept that the force and the distance have to be in the same direction. But how about an example like this, where you are supplying a force at an angle? Here's a person supplying a force at an angle. And so then, you know, the force that you supply is at that angle, but the motion is going to be parallel to the surface. So what you have to do here is you have to figure out what is the force, how much of that force is available in that direction, in that horizontal direction. So here it's only the x direction that matters when you're calculating the work. So let's see an example here. Let's see if you can figure this one out on your own. Maybe you can pause it and see, and when you come back I'll show you what my solution is. But I will tell you before I get going that the answer in a question like this would be, oh, actually the answer will come later. So why don't you give that a try, see if you can figure it out, and when you come back I'll show you my solution. Okay, well, welcome back. So let's see what we got here. First of all, the force in the x direction, we're back to vectors. So we could multiply the overall force by the cosine, and that's going to give us the amount of force that is in the x direction, which is the direction that the motion is going in. So even though they supplied a 55 Newton force, only 49.8 newtons is available to them. And work is force multiplied by distance. So there is our force, there is our distance, and there is our answer. How did you do? Were you able to get that one? All right, well, hopefully it makes some sense to you now. Okay, so power. The next thing we'll talk about is power. So power is, from a physics standpoint of view, the rate at which you do the work. How fast do you do the work? If we can both do 10,000 joules worth of work, but you can do it faster than I can, then you're more powerful, right? The faster you can do it, it's how fast you can do that amount of work. So power is going to be work divided by time. Now there is a lot coming at you in this relatively short video, and one of the things to keep track of is that there are a bunch of new symbols coming up here and a bunch of new units to keep track of. Now work I'm using as the capital W there, so that's what shows up in the equations. Remember that when we talk about weight, I try to make it a lowercase w, but it's very easy to confuse these symbols. T is the same old time that we've been dealing with, but it can get confusing with all the different symbols going around. Okay, so here's an example for you, and why don't you also pause this and see if you can answer the question, how much work was done? That would be the answer. And also, how much power was used? And that would be the answer. Why don't you pause and figure that out? And while you do, I'll turn the lights back on.
Oh.
All right. All right, well, welcome back, and let's see how we're doing here. Well, the work is the force multiplied by the distance, so I got the work by multiplying 250 by 30. There's nothing here to tell me there's any angle, so I'll just assume the force is in the same direction as the motion, and that gives me 7,500 joules. And then when I take those 7,500 joules and divide them by 40 seconds, I get the power. and the power is 187.5 W's. What? All right, there's another W showing up. Remember I said it was going to be a little confusing. Well, there is a derived unit for joules divided by seconds, and that derived unit for power is the watt. So the W here stands for watts. Watts are derived from joules and seconds. But you see how confusing it is? The W for watt shows up as the unit for power, but it's also the symbol in the equation when we're representing work. So this is very confusing. Once you get the hang of it, it's okay, but certainly confusing. Okay, so hopefully that helps you sort out all of these different letters that are coming your way. Okay, so let's try this one over here, and again, you can hit pause and then and try to figure it out. And when you come back, I'll show you the solution. Okay, welcome back. And here, yes, you got that happy person lifting weights. There's another way of doing it. And there is the work. Well, how did I figure out the work? Well, I'm going to tell you. What I did for the work was it's force multiplied by distance. So I multiplied the mass, the 35.5 kilograms, by 9.8. So 35.5 kilograms multiplied by 9.8 would give me the work, give me the force rather. And then if I multiply that by the distance 20, there's my work value. Now my question is how much power is involved. But go ahead, if you had some trouble before when you hit pause to get this number for the work, go ahead and make that calculation. Multiply your 35.5 by 9.8. That'll give you the force, that's the weight of the object. And multiply it by 20, and that'll give you the work, the force multiplied by the distance. And then for the power, you're going to take that work and divide it by the time, the 5 seconds for the time. So there we go. And you should have a full worked out solution in your notes so that you have something to go back to as I've described it. Okay, so here is our last example, and again, I'll give you a chance by pausing to see if you can figure this out, and then I will step you through the exact solution on this one. Okay, welcome back from your pause, and let's see if we can make sense of this problem. All right, there's my answer, 21.4 watts. Is that what you got, 21.4 watts? Well, let's see how it works out. First of all, this will be a full solution of the problem, so I'm going to identify the information that was given to me, and then I'm going to start showing my work that gets to the solution. So, first of all, I have to figure out how much force is available to me, and I'll do that by multiplying by the cosine of 40 degrees, and that means I have 53.6 newtons worth of force available. So, to figure out the work is force multiplied by distance. I will take that force available to me and multiply it by the distance in the same direction, and it turns out that the work is 1608 joules. So now I know the work that's available, the 1608 joules, and I can figure out the power, because power is work divided by time. The work is 1608, the time is 75, and that means 21.4 watts. There's another W for you. But a different W. See, the W in the equation up here, power is equal to work divided by time, is different than the W down here. But hopefully that makes sense to you. And if you have any questions, please bring them back to class, and I will look forward to seeing you there. Thanks for watching.